Great, recording is rolling. Welcome to Tuesday, December 7th. I have an exciting lab lined up for you guys today. Do you guys see those PVC pipes back there in that T shape? Right, and I've got that drawn here, this T shaped PVC pipe. Those can rotate about the central vertical axis. Right, this can spin. So uh, let me walk you guys through the mechanics of what's going on, then I'll show you guys what you're actually trying to figure out from this. Right, so uh, around this central vertical axis, there's tied a string. Now you can wind that string around this red pulley. I colored it red just because you guys have these red pulleys, so you can recognize what that is. Right, and then now that pulley itself is very low mass, very low friction, so we're going to assume massless and frictionless. And then you can hang a lab weight. Now, if you drop that lab weight, isn't this going to fall? And it's going to maybe pull on this at some radial distance from the central axis and cause this thing to rotate, like spin around. Right, that's how that would work, right? Let's play around with that in our minds. Think what kind of variables could you change and how would that affect the motion of this? For example, if you I've got to update this. If you increase this mass, do you think it's going to fall faster? Right? Actually, maybe that's not quite the right word. Let's distinguish velocity from acceleration. Right? Do you think it would accelerate faster? I mean, this thing would be accelerating, right? It could be speeding up, falling towards the floor. Right? Probably should be. Like, I bet there's a net force on this mass. That's what would drive it to move. If there's a net force, it's got to accelerate. F equals ma. Right? How about this? Do you guys see the arms on this PVC T-shape? Okay, you can actually pop these off. In fact, if you want to try this, you can. You can just pop these off real easy. You can just be like a vertical stick. Okay. What if you had that? What if you just had like a vertical stick and then you ran this whole thing? The motion of this would be different. Would that lab mass accelerate very quickly or very slowly towards the ground if you took off these arms? Yeah, you're right. It would be really quick. Huh. And that's actually getting closer to the idea I'm trying to lead you guys towards. This has something to do with rotational inertia. Okay, so if you do attach these arms on here, it will slow down the whole process. In fact, I bet if you even tied more mass onto the ends. Now, I don't have a space in the lab table. I'm going to show you guys a few minutes too. But if you did, I bet that would slow it down even more. Huh? Maybe because you'd be adding like more inertia, maybe more rotational inertia, right? And that's actually exactly where we're going with this. I want you guys to see if you can figure out what is the rotational inertia associated with this PVC pipe T-shaped structure rotating about this vertical central axis. And that is one of the conditions too. You have to say like which axis is it rotating about, because there could be different rotational inertia depending on which axis you're honed in on. Okay, so how are you going to get that? Now there's an empirical method I'm going to walk you guys through, but as a side thought, do you guys remember this table from your book on page 206 that has rotational inertia values for some common shapes? Okay. Take a look at this one right here. Maybe like a bar rotating about this central axis. Not about the end, like this one, but about the central axis. Okay. You guys see it says it's 1/12 ml squared, where L is the full end-to-end length, 1/12 ml squared. Okay. Huh. I bet you actually could approach this question from that point of view. You can say, well, this vertical central axis probably is not adding a whole lot of rotational inertia. Maybe it's negligible. I bet most of it actually is caused by this horizontal part of this T structure, like these arms. So you could say, what's the end-to-end length L? Find the mass of this whole thing, just that top part, and do 1/12 of the mass of those arms times this length squared, 1/12 ml squared. If you want to do that as a side thought and jot down that number, that would be some number of kilogram meter squared. That's probably pretty close to what you would get using this other method that I'm going to have you guys do empirically. Okay. Yes. Okay. So far with that setup. Okay. I should have had you guys grab one of these. This is clipped to the right side of your desk. This lab page you guys are using. Now there's a front and back half to it. The front is a table, like this 5-part table, and on the back is a space for a graph and also the final answer to this lab. Everything's leading to this very last box. It says I equals some number of kilogram meter squared. Thank you. Some number of kilogram meter squared. Right, so I'm gonna walk you guys through this so you guys know exactly what procedure to do, exactly how to do this thing. Okay. This lab's going to take a couple of days, so you guys get all day to do this. You might get like 2 or 3 rows, and then tomorrow I'll have you guys finish this. Okay, so today and tomorrow is allocated for this lab, and we'll start the midterm review on Thursday. Right, so let me zoom in here and let's see what measurements am I going to have you guys make, and then go step by step. Okay. So first column says radius in meters. Right, now there was some there was a question about this earlier. Which radius am I talking about? Okay. So I'm specifically talking about the radius of the central pipe. Okay. Here's why. Let me zoom in on that. Okay. So here's back up a little bit. Okay. Here's a zoomed in picture, right, of just not the whole thing, but just some of the essential parts. Okay. This string is going to be wound around the central axis. Right. Here's your lab mass swung over this pulley. It's going to pull down. It's going to, hey, if there's a tension in the string, right, because there's weight down here, there's tension in the string, at some radial arm distance from this true central axis, this dashed line going right at the center, isn't that going to provide a torque like R cross F? Right? So you have to know what the radius of the pipe is. It should be pretty close to a centimeter. Now, I'll let you guys measure that yourselves with either a ruler or a meter stick, but just as a ballpark idea, this radius should be pretty close to a centimeter. And if that's true, let's go back to this lab table. If you pay real close attention, I've given you guys all the fundamental SI base units, like kilograms, meters, and seconds. You guys see kilograms, meters, and seconds? Sometimes in your lab, I have you guys use like grams or centimeters or something, but not today. I'm having you guys use the classic fundamental units. So, guys, 1 centimeter is approximately how many meters? Is it 0.1 or 0.01?
0.01?
Yep, 0.01. Because 0.1 would be like 10 centimeters. Here's a ruler. Right? Here's 10 centimeters. That's 0.1 meters. Here's 1 centimeter, 0.01 meters, which is probably pretty close to this. Okay. So then next column, the lab mass that's hanging down says measuring kilograms. Now notice kilograms. Okay? So these lab weights have numbers stamped into them, and you just read that and use that. So this one says 200 grams. Suppose you have this one hanging, and that's what's driving the motion, okay, the weight of this guy. Now, it has a mass of 200 grams. So, guys, how many kilograms is that? 0.2. Yeah, because roll the decimal back 3 places. In fact, your guys' largest lab mass is 1 kilogram. So this number could probably go up to 1. There's probably some decimal, right? Okay. Then we get to a part of the table where, well, same having you guys do 3 trials and then take an average is sort of the deal. Okay. Maybe I should not have done that for this next column, but eventually you got to do it. So I want you guys to do like 3 trials, take an average. It's good for reducing experimental uncertainty, specifically random uncertainty. So like working with a stopwatch, we'll get to pretty quick. But the falling distance measured in meters. Falling distance measured in meters. Let's go back to the big picture. Oops, this one right here. Okay. So see that lab mass is going to fall some distance x. That's probably pretty close to 1 meter. Now it might be a little bit less than a meter, a little bit more than a meter. You know, maybe be depending on how many textbooks you stack up here. But this number should be pretty close to 1. It might be like 1.0, 1.1, 0.95, somewhere in that ballpark. Okay. Next column, time. How many seconds does it take for this lab mass to fall that distance? How many seconds? Now this one, do it 3 times, and so it should be pretty close to each other. Okay. Now, if you know, think what you know so far. You know the distance it would have fallen in meters. You know how much time that would have taken, and also starting from rest. Hey, is that 3 kinematic values? It sure is, which means that you should be able to calculate the acceleration of this thing falling. And it would be accelerating because there's a net force on it. Its weight down and the tension up are unbalanced. And so it would be accelerating, but how much? Well, let's go through the kinematic process to get to that. So, see, distance is a function of time. Do you guys remember this formula? X equals v naught t plus half at squared. You guys remember that? So distance is a function of time, sort of. And if it starts from rest, we can actually simplify this. Which of these 3 terms can you get rid of if it starts from rest? Oh, this guy right here. Because v naught initial velocity would just be 0, right? So let's get rid of that guy, just 0. Okay? So that's going to boil down to this. How far it falls starting from rest is 1/2 times the acceleration times t squared. Okay? You know what? I remember a story that was attached to this exact equation. Go into a mine shaft, California. Don't know how deep it is. Drop a rock. Takes 5 seconds for the rock to hit the ground. I wonder how deep it is. About 125 meters. You guys remember that? That's this one. This is the college equation. Now, he was using pure free fall gravity for that, which would if it was in free fall at the surface of Earth. But we're going to apply this sort of backwards. You guys know, or you're about to measure, how far does it fall and how much time. So you can back calculate what the acceleration had to have been. I mean, it's going to accelerate real slow all the way down, right? Okay. So cross multiply up 2, take the t squared, divide that down. Shouldn't the acceleration be 2 times the falling distance divided by the falling time squared? Like that? Is that true? Guess all that? Right. And if that's true, let's go back to this table. Notice I'm telling you guys which variables to measure and which ones to calculate and how to calculate. Hey, look at that. Acceleration is 2x over t squared in meters per second squared. So you have everything in meters and seconds, right? Remember the maximum value of this would be about 10 meters per second squared. That would be pure free fall. You guys would probably get something much smaller than that. Okay? All right, next column, tension. All right, so let's go back to take a look at this. Right? So this lab mass is going to have 2 forces on it. It has a weight pulling it down, but there's also the tension pulling up. And I'd like to know the tension because that tension is going to be the same tension routed over here that's going to cause a torque that's going to cause this thing to rotate. Right? So yeah, we definitely have to figure out the tension. Okay. Let's go to, actually we just sort of did the kinematic review, didn't we? And here we're going into this midterm. A bunch of these old concepts are all coming back in. All right, we're doing rotation right now. That's the theme of the lab we're doing. Here's a kinematic review. We're about to do a dynamics review, like with forces and Newton's laws of motion and free body diagrams. You guys remember all that? So say I have a lab mass right there. So FBD, free body diagram. I'm thinking 2 forces. There's a weight pulling straight down. I'll call it mg. And there's the tension holding back up. I'll call it capital T. Okay? And notice how you made those unbalanced. Right? So there's a net force. Do you guys remember net force is equal to mass times acceleration? That's due to the second law of motion. Okay? And what is the net force? Well, it's just the difference between these two. So the weight down minus the tension up, let's call it down positive. So that would be consistent with that. Right? Then this acceleration could be positive. Right? So that net force results in this mass accelerating some amount. I'd like to know what is, oh no, I'm so sorry, not that one. Scratch that. I'd like to know what this tension is. What is this tension? You guys would have calculated acceleration already using kinematic motion, right? Kinematic equation. So let's solve for this tension. So add this over, subtract this over. Tension is going to be the weight minus m times a. Can that be true? Okay. And then, if you wanted to, you could even factor out the lab mass and get g minus a. Right? M times g minus a is the tension. Oh, hey, you guys have seen this before. You guys remember tension in an elevator cable? Remember tension in an elevator cable is m times g plus or minus a? If it's accelerating up, you do plus here. If it's accelerating down, you do minus here. Hey, and that's exactly what we got. This is sort of like an elevator accelerating downwards. Okay? The tension is a little bit less than the weight. The weight is mg. The tension is a little bit less than that because there's a little bit of slack in the line so that it can accelerate down. Okay? And that is the next column. I have you guys calculate right here. It says tension m times g minus a. That's exactly what that says. Okay, so getting pretty close to the end of this table. Next column, angular acceleration. Okay, so this is the rate that this PVC pipe structure is speeding up spinning. That would be angular acceleration, right? Well, that is directly proportional to the linear acceleration of the slab mass falling. Okay, the slab mass falling, there's physically a string that's tied to this central axis that's causing this thing to spin. Do you guys remember this connection right here? Right? Actually, let's review all 3 of these. Right? So how far does the lab mass fall? X. How far does the PVC pipe structure rotate? That's theta. Hey, that's related to this R. Remember, this R is approximately 1 centimeter, so you can call that about 0.01 meters. I'll have you guys do a direct measurement. It might be a little bit different than that. Okay? That's what that is. Recorded on your lab table. Okay? How fast is that lab mass falling? Now, this is a changing number, but that's equal to how fast this thing is spinning times the radial location, or radial distance of the central axis. Okay? And then here's the relevant one for the column we're looking at table now, which is if you want to figure out how fast the structure is speeding up spinning, that's alpha, radians per second squared, angular acceleration. Take the linear acceleration of the lab mass and divide by the radius of that PVC pipe. that central vertical axis, right? Okay. And that's exactly what this says to do right here. It says angular acceleration alpha is equal to a divided by r, and that'd be measured in radians per second squared. Okay, you guys got that? In the last column of this lab table, torque. So torque, you guys know, is r cross f. So the radial distance in this case is the radius of this PVC pipe, and the force is the tension in this line, which remember is a little bit less than the actual weight of the lab mass, but you guys would have calculated this by this point. So this tension and this radial distance, r cross t, right? Multiply those two together, you get a torque in Newton meters. Okay, right? Okay, so now that's just a bunch of pure values for a table to fill out the table. Some things that you measure, these first few columns, some things that you calculate based on those measurements. Okay, but you guys got all these physical quantities, right? Okay. Also, switch out the lab masses. So you have 1, 2, 3, 4, 5 different lab masses. This is going to take a couple of days, right? Okay. And then take some averages. So you have an average angular acceleration alpha and an average torque value tau in Newton meters. Okay. Right. Now, once you got those two, I'm gonna have you guys treat these like XY coordinates, like XY, and plot those on this graph. Now, this is on the back of your guys' lab page. Okay, that says tau versus alpha, torque versus angular acceleration, Newton meters versus radians per second squared. Okay. Now, why would I want you to create that graph? I'll take you guys through why. So, let's go torque and Newton meters as a function of angular acceleration and radians per second squared. Okay? Now, cause effect to make more intuitive sense to do that backwards, but there's a reason I'm gonna have you guys do these axes this way: x-axis, y-axis. Okay? You're probably, I have a prediction what your graph is going to look like. It's probably going to look something kind of like this. Okay? I bet your points are all going to line up in a straight line. And I might be wrong about this, but I think you're probably also going to get a y-intercept here. I might call this like tau naught or something like that. Okay? I'm sort of giving away the end of this lab, but there's a reason to do this. I want you guys to see the broad picture of like the textbook walkthrough, how this should work out, and then see, does it actually, like empirically? Okay? Let's think about torque. Now, you guys know torque is r cross f, of course. That's the way I introduced it to you guys, and that's one of the calculations you're doing in the lab. But there's another formula for torque. Do you guys remember what the other formula for torque is? Torque equals what times what?
I times alpha.
Boom! I times alpha, right? Remember, this is analogous to F equals ma, right? What Newton's second law of motion says: if you put a force on something, it causes something to accelerate. How much? Well, it's inversely proportional to its mass. This says if you put a torque on something, how fast does it cause it to speed up rotating? Well, that's inversely proportional to its rotational inertia. Right? Now, does this look kind of like y equals mx? Right? Hey, y equals mx. So if that's true, and alpha is your x value, or x-axis, and tau, torque, is your y-axis, hey, this looks like that does. And what property of this graph would represent I? The slope. Exactly, the slope. Right? So that would be like this right here. We call this I, like torque equals I times alpha, like y equals mx. The rise over run. Right? Okay. So that would be your last step to figure out what is the rotational inertia of this empirically. Like I said before, if you'd like to, you can compare it to the textbook, like 1/12 ml squared, see how close that is. Okay. One last detail I want to mention here is take a look at this y-intercept, right? Say like a tau naught. Right? Maybe I should modify this equation a little bit and say the net torque equals I times alpha, kind of like net force equals mass times acceleration. Okay. Now, I don't want to give it away here, but I want you guys to think about this. Just plant this idea, have you guys think, why would there be a y-intercept here? Why would there be a tau naught? See if you guys can figure that out. Or even if it does exist, because you might not get one. You might just get through the origin. Okay, but I'll let you guys figure that out. Okay, you guys got any questions? All right, so go ahead back there. Everything you need. Back to lab stations. I'll walk around, help you guys out. And you guys got today, tomorrow. Yeah.
Do you have any tissues?